Hey everybody, in this video we're going to introduce thermodynamics, and at the end of this video you should be able to calculate the heat transfer in a substance and be able to use the formula Q equals mc delta T in order to calculate those values. So what is thermodynamics? Thermodynamics really is the study of how energy is transferred in a chemical system. There's kind of a lot of, there's a lot that could be, but typically we're talking about heat energy, okay? And so energy is the ability to do work. That's the kind of the physics definition of what energy is. And in order to do work, things have to move. So when we're talking about chemistry, we're talking about the movement of molecules, whether they're colliding or colliding with enough energy to cause a reaction to occur or whatever. Okay, and so but energy is required to make things move. Now there's two types of energy that we worry about. There's kinetic energy, which is like kind of the standard sort of energy that we think of, like when atoms are moving and cars are flying down the street, or maybe even electrons flowing through a wire. But there's also potential energy, which is the energy that of something that something has that's stored that could potentially be used to cause motion. Okay, so if you take a soccer ball and hold it over your head, that is an example of potential energy. That soccer ball, because it's being held at some height above your head, has stored energy. Chemical bonds are not moving, and so they're storing energy. And another chemical example is when we have two either oppositely charged or similarly charged ions or particles, the attractive forces or repulsive forces, they store energy. So there's all sorts of ways that we can store energy. We're going to focus primarily on those that deal with chemistry. Okay. One of the important things to keep in mind is that no matter what, energy is always conserved. So no matter what happens, whether we add a whole bunch of energy to a system, the first law, this is actually, let me write that down here. Okay, this is what we call the first law of thermodynamics. Okay, and so in the first law of thermodynamics, the energy in a chemical reaction is always conserved. And if I can, for just 1 second, I can tell you that energy equals mc squared. This is Einstein's famous equation. There's a lot more to it than this, but keep in mind that mass is a form of energy, or mass is related to energy. So it's kind of interesting that, and you may have even heard this in previous classes, that mass is conserved. Well, since mass is a form of energy, it's really that we're saying that energy is conserved. And so in order to understand how this works in chemistry and thermodynamically, we really have to talk about the difference between temperature and heat. Okay, so the difference is that heat is the energy itself. Okay, heat is the thing that will actually cause the molecules to move around. And temperature is a measurement of that ability to transfer heat. So temperature is really the measurement, or maybe the effect of the heat, and then heat is the energy itself. There's subtle differences, but keep in mind usually we add heat to a system by increasing the temperature. Okay, right? Okay, so we typically don't add temperature to the system by changing the heat. So it's subtle differences, but I need to make sure that I go over them so that everybody's all on the kind of the same page. So another set of definitions that we need to talk about is the system versus the surroundings. So a system is the object, and in this case we're going to keep it very specific to the chemistry realm. We could talk about, physics and astronomy and, what the system is. But in chemistry, the reference when we're transferring energy is always the system. That is where the reaction is occurring, okay? So if we're looking at a reaction, the system is the reaction itself, okay? And so when we have a positive energy, that means that the system, again, look at it from the point of view of the system is gaining energy, okay? And because we're dealing with thermodynamics, typically we're talking about heat energy, okay? And so if it's negative, again, consider it from the point of view of the system. That means the system's heat energy is negative, or the transfer of heat energy is negative, and so therefore the system is losing heat energy, okay? And now the surroundings then is everything else. So if you have a reaction, if you're doing something in a beaker, the reaction is in the beaker, the system is in the beaker. The surroundings is everything else. Now, we can be really silly and we can talk about everything else, everything else like out to Pluto or the moon or things like that. Yes, the whole universe is the surroundings. But typically, we only talk about the surroundings being those things that can reasonably transfer energy to the system. Okay, so that's why I say it's usually the things that are just close to it, is because when we're talking about surroundings, they're the things in the immediate area that can add energy to the system. Yeah, I get it. The sun is where all the energy comes from. That's all the way away, so yes, we can talk about all the exceptions and all the craziness, but I just need to get you a perspective, okay? So I need to get you kind of all on the same page. If we're doing a reaction in a beaker, okay, this is your system, and everything kind of around the outside, I'll change my color here, everything kind of around the outside is the surroundings, okay? And so all of this, because heat or energy can transfer between those two things. Okay, so that kind of sets up the basics of thermodynamics, okay? We're talking about how energy, specifically heat, is being transferred around. And so there has to be some measure of how well something can transfer heat, okay? And so that's what we use specific heat capacity for. The specific heat capacity is how much energy something needs in order to raise 1 gram of that substance by 1 Kelvin. Okay, and the standard has always been water. So how much energy does it take to raise 1 gram of water, 1 Kelvin? It takes 4.18 joules to do that. Okay, so everything is kind of based on water. Okay, but it depends on a couple other things. If we have more water or more, that's going to affect how much energy that can be transferred, because if we have more something, more energy can be transferred. It also depends on how the temperature changes. It provides for the ability to, by increasing the temperature, changing the temperature, it provides for the ability for more heat to be transferred, or less heat depending on which way the temperature is changing. Okay, and also you can imagine that the type of material matters. If you touch a piece of metal versus a piece, water. Let me back off that description. Let's say you're boiling water on the stove. Okay, well, the water takes forever to heat up, but the pot that you're boiling the water in doesn't. It heats up rather quickly. So that's because the metal has a lower specific heat capacity. It's able to heat up more quickly. It doesn't need as much energy to raise the temperature 1 Kelvin. Okay? And so the formula that relates all of these quantities together is Q equals mc delta T. And so for any of you who are going to be a doctor, okay, the MCAT is the standardized test that's an entrance exam. It's the what is it? The medical something aptitude test. Okay, so and so it's kind of funny that the MCAT test and MC delta T, they look a lot alike. But Q is the heat energy that is transferred. It's how much heat is being transferred in the reaction. Okay, and then you have the mass, which is typically measured, in this case it's going to be super weird, but we're going to usually measure it in grams. C is that specific heat capacity, which is a given, and that has units of joules per gram Kelvin. Okay, and the change in temperature is measured in Kelvin. And remember, anytime it's a change in anything, you always use final minus initial. I guess I should tell you that heat energy, or energy, any energy, whether it's heat energy, electrical energy, potential energy, kinetic energy, electrical energy, whatever kind of energy you're talking about, energy is always measured in joules. Okay, so that C, we've kind of already addressed this, but that C, that specific heat capacity, is a constant. There are tables of specific heat capacity. Okay, just for convenience sake, I have one here. Okay, so if we look here, here's a whole bunch of specific heat capacities. Notice that water is has the highest specific heat capacity of any of these things. Okay, water takes the most amount of energy to raise its temperature by 1 Kelvin, or 1 gram of it by 1 Kelvin. Okay, notice that the metals here are all much smaller than water's specific heat capacity. Okay, aluminum is 0.9. Copper, gold, they're all very small. That just means that it takes a lot less energy to raise the temperature by 1 Kelvin. Okay, so you would say that gold can get very hot very quickly. Although time is usually not a factor, it just means that it takes less energy to raise the temperature. So that's that. Okay, and so that's kind of what I was talking about here. And this is kind of the practical, applications. Again, quickly and slowly, we're not talking about a kinetic situation where we're talking about speed of a reaction or anything. But that's kind of the practical application. If something gets very hot very quickly, it means it has a really low C. And then if something takes a long time to get hot, or doesn't get hot very quickly, that means that it has a very high C. Okay. Oh, that's not a high C, but that's close. It's not even close. Sorry.